Let's approach Shannon entropy from a different perspective. Consider a scenario where Alice communicates with Ava through an electrical wire that can only transmit ones and zeros. They want to send messages composed of 4 symbols, A, B, C, and D with the following probability distribution. To encode these symbols, they use the following coding scheme. Thus, the message would be coded as using 22 digits. Since the probability distribution is non-uniform, a more efficient coding scheme could be. Therefore, the same message would be uniquely coded as, which is 19 digits long. This coding scheme works well, because assigning shorter binary strings to more frequent symbols and longer binary strings to less frequent symbols helps reduce the overall number of digits needed to encode the message. How do we find the optimal coding scheme? This problem is not related to our machine learning topic, but I am very curious. So I formulated the question and asked ChatGPT for an answer. Given a random variable x with values 1, 2, 3, 4 and corresponding probabilities of 1/2, 1/4, 1/8, 1/8. The goal is to assign binary codes to each value to minimize the average number of bits in the sequences of x. My question is, how can this be achieved? I am not going to show you the whole answer. You can formulate your own question and ask ChatGPT for yourself. In summary, entropy is a measure of the smallest possible bit length, theoretically achievable for a given alphabet, with associated probabilities. Huffman coding typically approaches the entropy value. One of the things that is hard to quantify is information. It may be surprising to learn that information is related to surprise. A high probability event has low surprise, while a low probability event has high surprise. An event that is 100% predictable holds no surprises. To put it another way, if a highly likely event occurs, the message carries very little information. On the other hand, if a highly unlikely event occurs, the message is much more informative. For example, consider a weather forecast with 3 possible outcomes for a summer day: rainy, sunny, and snowy. Waking up to heavy snow on your doorstep would be quite surprising. How do we measure surprise? If surprise is defined as inversely proportional to the probability of an event, an increase in probability would typically result in a decrease in surprise. However, Claude Shannon introduced a more effective measure. His definition was selected based on several axioms. 1. An event with a 100% probability is completely unsurprising and provides no information. 2. The less probable an event is, the more surprising it is, and the more information it provides. 3. When 2 independent events are measured separately, the total surprise is the sum of the individual surprises. This definition does not meet the above requirements. Shannon's measure of surprise is based on the logarithm to the base 2. According to Shannon's definition, we can calculate the surprise for the events rain, sunny, and snow. and then calculate the average surprise based on the probability distribution. Shannon entropy measures the average surprise of events, based on their predictability. Suppose we have a random variable x, with n possible outcomes. The probability of each outcome xi is given by the probability pxi, such that the total probability over all outcomes is 1. Shannon entropy is formally defined as Now, let's discuss cross-entropy using the example of a four-sided die. In this scenario, we assume the die is biased, but we approach cross-entropy based on the assumption that the die is fair, as it appears to be fair. Our key questions are, 1. What is the surprise value of an individual event? 2. What is the average surprise value? To address the first question, we compute surprise values assuming the die is fair. For the second question, the average surprise hinges on both individual surprise values and event frequencies. Despite our assumption of a fair die, the die's bias remains, and the probability distribution P dictates event occurrences. Therefore, the average surprise is the weighted sum of individual surprise values based on the probability distribution P. If the distribution Q changes, the surprise values of individual events change. We can calculate the average surprise to be 2.625. This graph displays various cross-entropy values for different probability distributions, Q. If Q equals P, the cross-entropy value reaches a minimum. Let's explain cross-entropy using the same yes or no question game. For a given probability distribution P, entropy represents the minimum number of yes or no questions needed to determine the outcome of rolling a die. The optimal strategy involves dividing the yes or no answers evenly, to minimize the number of questions required to reveal the outcome. By calculating the minimal number of questions needed, we can determine the efficiency of the guessing game. If we are uncertain about the true probability distribution and instead consider a different distribution Q, we would adapt our questioning strategy accordingly. The number of yes or no questions required for each event can be calculated using the formula minus log Q instead of minus log P. As we have seen, our questioning strategy based on Q does not change the fact that the distribution P determines how often an event happens. Therefore, P is used for calculating the average number of questions needed. The final result is cross-entropy. If we change distribution Q, the strategy will be changed accordingly. In this way, we arrive at the formal definition of cross-entropy.